All right. So the next thing that we're going to do now, we're going to calculate. So this is mode 1 of failure before the break. And we realize that if the load P is going to go beyond 6910 pounds, okay, our fastener will fail due to the shearing force, and this is due to the spacing and the force resistance of the bolt. So the next thing that we look at is the next thing that we're going to look at is the we're going to calculate mode 2. And so mode number 2 is failure of the wooden structure. And we are aware, okay, we know, and we are aware that the failure will occur at the centroid. Why at the centroid? Because at the centroid, is where tau max will occur. Okay. So the failure criteria, we know that the shear allowable is equal to 3 times 10 power 3 psi. We know that, right? So this is given, right? This is given. So from here, we know that to calculate the shear, given that the shear allowable, this is equal to V Vy over Iyy, sorry, Izz, right? Izz Qz divided by T. Okay. So the Qz over here, I'm going to put Qz at its what? Maximum. So going back to the structure over here, right? Knowing that this line I'm going to draw, this is our centroid, and this is where failure will occur also. Okay, failure will occur. Right, so we're going to calculate our Q. So the Q max will be the Q of the wooden member plus the Q of the web. Okay, and the Q of the wooden member we have calculated earlier is 168 plus by 2. The 2 down here is because of left and right web. Okay, you have, so the width is 0.5 inch, right? So we know the width is 0.5 inch. The depth is 9, right? 5 plus 2, 2. Okay, so 0.5, 0.5. The depth is 5 plus 4, right? And then the Y bar, right? The Y bar is, so 5 plus 4 divided by 2. Okay, so this will be equal to 168 plus by 2 times 0.5 times 9 times 9 divided by 2 is equal to 40.5. So 168 plus 40.5 is equal to 208.5. inch cube. So now we can calculate. So the T over here, right? The T is 0.5 inch, but you have left and right also. So the shear allowable is 3 times 10 to the power 3. The V is P over 2. The I, we calculate, not I calculate, it's given is 2902. Right? And then the QZ max is 208.5. The thickness is 0.5. You have to put 2 down here because you have left and right. So you have 3 times 10 to the power 3. So this will be equal to 208.5 divided by 2 divided by 2, 902 divided by 0.5 divided by 2.
Eugene,
Yes.
why are we dividing by 2 twice?
I'll need divide by 2 once. Why got twice?
There's the P divided by 2, and then
Yeah.
there's the 2 on the bottom.
So this is because of what? Question for you now.
The reaction forces.
There you go. It's not the same, is it?
No.
Right?
Yeah.
Right? Am I right?
Yeah.
Okay. So from here, your P is equal to 3 power 3 times by 11608 divided by 417. It's equal to 83.511 times 10 to the power 3 pounds. So it's proven that if you just consider the strength of the wood, it can withstand much higher P. So therefore, the P that we calculated earlier, which is 6910, is the maximum allowable force. Okay, so if this structure is going to fail, it's going to fail due to the what? The fasteners. Okay, not due to the wooden structure. The wooden structure is significantly higher. Okay, it's about more than 10 times higher, right? So if you want the fastener to, if you want to like increase the load, right, by not changing the wood, things you could do is you can use thicker diameter fastener. You can also distance the spacing. Okay, reduce the spacing. That will increase it. Now, question for you: if based on shear, where just based on shear alone, okay, we're not talking about normal force or what, just based on shear alone, where will the structure fail? Can anyone tell me? Can anyone make a guess? Where will it fail? Yes. Anyone? Is it going to be 2 feet from point A? Is it going to be exactly at P? Or is it going to be 1 feet from point B? Anyone?
It's P.
It's going to be, okay. You are saying P because P is there, right?
In the middle.
In the middle. Based on shearing, does not matter. It can fail here, 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 it can fail here. Why do I say that, anyone? It can fail in any of those paths, not necessarily at P, if based on shear alone. Okay?
Because the vertical shearing forces is P and the negative P.
You're partly right. This is because if you look at the shear force distribution, right? If you look at the shear force distribution, right? P max is equal to P over 2. So P max, it can be anywhere. It can be here. It can fail. It can be here. 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 Okay? So that is the reason. For just on shear alone, if we include bending moment, it's definitely going to be in the center. Okay? If it's bending moment, if we include bending moment. Any questions so far?
I have a question on the spacing of bolts.
Yes.
So wouldn't the spacing of bolts, wouldn't you want a smaller spacing to
Yes.
increase Q?
Yes, yes.
Okay,
You're
so
right.
you're saying it the opposite way. You're saying a larger spacing will increase Q.
No, to increase the P, you reduce
Oh.
the spacing.
Okay, smaller spacing, right?
Yep, smaller spacing. But you have to remember, once you start reducing your spacing to make this structure, the time increases. Yes or no?
Yes.
So is it better to increase the spacing, or reduce the spacing, or is it better to use a bigger diameter bolt so it can hold? So there's a trade-off. Yes or no? One is
Yeah,
a material cost, is a weight. Okay, so there's always a trade-off. That's where we do optimization, right?
Eugene,
Yes.
wouldn't that increase stress concentrations if we put more holes into the wood?
Yeah, right. It will increase stress concentration, but the fastener will still fail first.
Okay.
Okay. Right. So this is an interesting problem, right? This is one of the problem. This is like a this is a backbone when I do consulting for calculation for landscaping company that builds a deck that is going to be 6 feet tall at least. They need to show to the CT this set of calculation. So this is what I usually do, but in 3D. Okay, so later on at the end of this course, when you do 3D analysis, you guys will be able also do the same, right? So my objective at the end of this course, you are brave enough to design a bridge, not just the looks. It can be really ugly, but it have to withstand the stresses. All right. Now let's look at another question now. Okay, so example number 2. So this example, I'm not going to change. Okay, so this example, we're not going to change our rules at all. The rules still stand. Okay, everything still apply. Okay, so as I said, you can get this on Avenue. So example number 2. And you'll see like, hey, nothing changed. Okay, and then right. So this is our structure now. Okay, so it's not exactly the same. So the box beam, so this is called a box beam, is constructed from 4 bolts that are fastened together using nails, spacing along the beam every 2 inches. So every 2 inch, we have a nail. So we have S is equal to 2 inches, right? And force resistance of the nail force resistance of the nail is 50 pounds. Okay. Determine the greatest V that could be applied to the beam without causing failure of the nail. Right. Okay. So this is our section. Right. We are still going to apply the same 4 rules. Okay. So I'm going to give you, I'm not going to calculate I. I'm just going to give the I value. So I is equal to 197.7 pounds. Inch to power 4. Now, can anyone tell me how they measure the force resistance of the nail? Anyone? You have to know. Anyone? Let's step aside. Let's think. How do they measure? Anyone? By breaking it.
Apart.
Huh?
Start pulling it apart.
Yeah. So what is going to happen is I'm just going to sketch this, okay? right?